Hi, I'm Amy Flicksteiner, and this is Elementary Algebra. I am your instructor for this course, and we're going to work today on Chapter 5. Chapter 5 is titled Polynomials. We're going to manipulate and work with some exponents, bases. We're going to learn about some terms and what a polynomial is, how to manipulate them. All right, so let's get started. So we're going to begin by looking at bases and exponents in what's called an exponential expression. For example, if you see something like 7 to the 5th power, this is an exponential expression. 7 is our base. That is the number that is a factor. 5 is our exponent. Sometimes we say 7 to the power of 5, and that means the same as 7 to the 5th, or 7 with a power of 5. So I got a spelling error here. There we go. 5 is the exponent, 7 is my base. All right, so what does this mean? The exponent tells us how many times 7 is a factor, or how many 7s there are being multiplied together. So 7 to the 5th means 7 multiplied by 7, multiplied by 7, multiplied by 7, multiplied by 7. This number is really large. We often use a calculator to find it. If you have the recommended calculator for this class, we would start by writing or typing in the base of 7. And then we want the caret key. That's this key right here. It's an upside down chevron, 7 to the 5th. And this does mean 7 times 7, which is already 49, times 7 again, which is going to get us 345, I think, right about then. And then we're going to multiply that by 7 again, which is going to be over 2,200. And then we're going to multiply that by 7 again, which is more than 2,000, more than 14,000. So when I type this, I expect to see a very large number when I hit enter. And I do. I get 16,807. This is known as standard form. 16,807. So 7 to the 5th would be our exponential form, and 16,807 would be what we call the standard form, right? An example, we're going to have to be able to identify the base and the exponents in each of these examples below. It's not quite as easy as you think. So when we're identifying the exponent and the base, the exponent here is 3. The base is what's being multiplied. Without the parentheses, that negative becomes a part of the problem, but irrelevant to the exponent and base. This would be a base of 6 with an exponent of 3. 6 to the 3rd power, negative. So the negative would come last. The difference here is with number 2. Do you see how number 2, they put the parentheses around it? That gives us a base of -5 with an exponent of 3. Okay, the parentheses keep -5 as the entire base. So the parentheses tell us we want both the negative and the 5 being raised to the power. Number 3, we have a -6 to the 4th. Again, without the parentheses, the 6 is being raised to the 4th power. So our base is the 6. Our exponent is the 4. The negative would just be put on at the end. This is different from -6 to the 4th. Again, the parentheses tell us that -6 is the base with the exponent of 4. Similarly, if I have 5x to the 4th, that 5, order of operations, comes last. I have x as my base with an exponent of 4. Once I have x to the 4th, then I would be multiplying it by 5. That is not a part of the base, nor is it a part of the exponent. However, when we look at the next example, the parentheses tell us I want both 4 and y to be the base. By putting the parentheses around them, I'm telling the world that the 4 and y are one unit together. There is an exponent here of 3. Okay? All right. The second part of this is, can you write or use the exponents to write the exponential expression? Here I have a negative 3 times 3 times 3 times 3 times 3. The negative is only being used once, so it is not a part of my base. What is being multiplied over and over and over again is the 3. And that 3 is being multiplied 1, 2, 3, 4, 5 times. So as an exponential expression, this would be 3 to the 5th with the negative hanging around out front. Similarly, for number 8, I have an x being multiplied 1, 2, 3 times. So this would be x to the 3rd times the y is being multiplied twice, y squared. This would be x to the 3rd, y squared. Number 9 is slightly different in that it is actually a negative 2 that's being multiplied over and over and over again. So in exponential form, I would want to put both the negative and the 2 inside parentheses to show the world that it's not just the 2 that's being multiplied over and over again, but also the negative. So this would be a negative 2 to the 1, 2, 3rd power times c to the 3rd power. In exponential form, this would be negative 2 to the 3rd, c to the 3rd. Right? The fourth example shows us what happens when we put the 2c together and we multiply that 2c over and over and over and over again. In exponential form, this would be 2c to the 1, 2, 3, 4th power. 2c to the 4th. Okay? Perfect. Our second goal in this is that we are going to learn the first of the rules for powers and exponents. This is known as the product rule for exponents. And it says, if you have two bases, I should have said two like bases. Well, we'll just say two bases that are the same. And they are being multiplied together. The exponents can be added. What does that look like? Well, the generic algebraic rule basically says if you have x to the m power and you multiply that by x to the n power. Here I have a base of x with an exponent of m. This one has a base of x with an exponent of n. This is the same as x to the power of m plus n. So I can add those two exponents together. I have m with this x and n with this x. The base stays the same, and the exponent becomes the sum of the two. Right? Some examples. Here I have 5 to the 3rd times 5 to the 6th. The bases are the same. So that means that this would be the same as 5 to the third plus 6. I can add those two exponents together. 3 plus 6 is 9. This is the same as 5 to the ninth. I can figure out what 5 to the ninth is, but the instructions say to go ahead and answer using exponents. So I'm going to leave it as 5 to the ninth, right? The second one is 2 to the third times 3 to the sixth. In order to use the rules, are the bases the same? This one has a base of 2 to the third power times a base of 3 to the sixth power. The bases are not the same. And because the bases are not the same, the rule cannot be used. We just got to leave it. There's nothing that we can do here. All right? So watch out for those when the bases aren't the same, even though they're all exponents, because there's nothing you can do here but rewrite it. Just leave it as 2 to the third, 3 to the sixth. Can't do anything else with it. For number 13, I have a to the fifth times a. For this guy, you have to be able to recognize that a to the fifth is a to the fifth power, or a times a times a times a times a. That's what a to the fifth is. It's a as a factor 5 times. And then we've got one more a. That's this one, right? So this a here is just this last a on the end. And these 5 a's here all account for a to the fifth. So this gives me 1, 2, 3, 4, 5, 6. This should be the same as a to the sixth. Now, how can I shortcut this a little bit? Do you see this a? See how there's really just one of them? If I look at that as 1a to the first power, as in 1a, then I can use a to the 5 plus 1. And make sure that that rule still fits here. But I have to be able to see that 1. Okay, let's try another one. Number 14 says y to the third times y squared times y to the eighth. All of the bases are the same. So this is going to be the same as y to the 3 plus 2 plus 8. I can add all of those exponents together. If the bases are the same, the exponents can be added. 3 plus 2 plus 8 is y to the 13th. What about 15? 15 is a little bit different because we've got C's and D's. So the idea here is to rearrange, because remember, multiplication is commutative. I can move stuff around. So I can do this as C to the third times C times D to the seventh times D squared. Now, just like in number 13, I have to be able to see that C without an exponent as C to the first, right? Because there's one of them. So that's going to give me C to the 3 plus 1 times D to the 7 plus 2. D and D are the same base. C and C are the same base. This gives me C to the fourth times D to the ninth. That's it. That's how I can manipulate it. Okay, let's look at number 16. Number 16 is interesting because we do have parentheses. In the first set of parentheses, we have a plus b. That means that a plus b is being protected and it goes together. Similarly, we have a plus b to the fifth. A plus b to the fifth, right? They're exactly the same. The base here is a plus b. The base here is a plus b. I mean, it's like carrying a mess in a backpack, but it's the exact same mess. It's the exact same mess, exact same stuff. So this would be the same as a plus b to the 2 plus 5, or a plus b to the 7. Right? Same rule, used multiple different ways, giving you several different examples. Let's take a look at the next rule. Because you know one just going to be one, right? We were going to put a bunch in there today. You knew that was going to happen, I hope. All right, the third goal is dividing exponential expressions that have like bases. This is known as the quotient rule. Quotient is another word for division. So, if two exponential expressions, that's how I want to say it, exponential expressions with the same base, there we go, are divided, those exponents can be subtracted. This is put together like if you have an x to the m over an x to the n, this would be the same as x to the m minus n. Notice we're taking the top exponent minus the bottom exponent. And that's always going to be true. It's always going to be the top exponent minus the bottom exponent, right? You have to, again, have the same bases. So if we're looking at number 17, in the numerator, the base is 13, and in the denominator, the base is also 13. Since the bases are the same, I can rewrite this as 13 to the power of 11 minus 2, or 13 to the 9th. I'm going to leave it in exponential form. 13 to the 9th power is 13 times 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 13. It's a crazy amount of 13s. Oops, 13 to the 9th power. Yeah. To the 10th. So hundreds, thousands, millions. This is like almost 11 billion. That's what this number says. It's nearly 11 billion. That's a big number. All right, let's do number 18. Number 18, do they have the same base? Well, the base in the numerator is x. The base in the denominator is x. Since I do have the same base here, I can take that base of x and I can subtract my exponents, 8 minus 3. This would be the same as x to the 5th power. How does this work? Well, this is a good one to show you how it works. So basically, we're just canceling factors. If we were to do this the long way, writing it all out, that's going to be x times x times x times x. 5, 6, 7, 8. Right? That's x to the 8th over x to the 3rd, which would be an x times an x times an x. And what happens here is that we can cancel. We can eliminate this x with this one, this x with this one, and this x with this one. These have all canceled as a 1, leaving me just a 1 in the denominator. And 1, 2, 3, 4, 5. So I would have x to the 5th over 1 if I wrote everything out, which would just be the same as x to the 5th. And this is great. It's a fantastic way to do things, but I didn't want to write out 11 13s. If I do it the long way every single time, it's a lot of work. So what's the shortcut? The shortcut, or the rule, the pattern, if you will, is subtraction. Okay? Let's take a look at number 19. Number 19, we actually have 2 different bases. I do have a y and another y here. That is the same base. So this would be y to the 4 minus, is that a 0? Nope, we talked about this. There's not an exponent on there. There should be a 1. We should put a 1, so that will be y to the 4 minus 1. And then if I take a look at the z's, here I have a z to the 8th and a z to the 6th. That is the same base, so I can take z to the 8 minus 6. This will give me a y to the 3rd, z to the 2nd. Y's and z's are not the same bases. They're not the same letters, so I can't do anything more to simplify. That's the best I can do. Y to the 3rd, z to the 2nd. With problem number 20, we have 3ab to the 5th over 3ab to the 2nd. You see those parentheses? You see how it hugs all of 3ab, both in the numerator and in the denominator? That tells us that they go together. They will stick together. In the numerator, I have 5 of them. In the denominator, I have 2 of them. And since they are the exact same base, I can say this is 3ab to the 5 minus 2 power, or 3ab to the 3rd. And to keep it written in exponential form, I will use that exact answer. Right? Did I go with difficult ones? All right. Moving on to the next rule. The next rule is what happens when you raise an exponential base to another power. Here's what happens. When an exponential expression is raised to another exponent, the exponents can be multiplied. All right, so that's our patterning. That's our shortcut, is that we can multiply them. What does that look like? If I have x to the m power, and I use that exponential expression as a base for another exponent, so x to the m raised again to the n, this is the same as x to the m times n. I can multiply those two exponents together. Let me show you with some numbers, just to demonstrate the pattern. If I have 7 to the 3rd to the 5th, this outside exponent means I'm writing 7 to the 3rd 5 times. 7 to the 3rd, 7 to the 3rd, 7 to the 3rd, and another 7 to the 3rd. That's what it means, right? That exponent means I'm writing this base 5 times. So what do I have? Well, now these are all being multiplied. And I know from my previous rule, when I have a base being multiplied, right, the same base being multiplied, I can add. So this would be 7 to the 3 plus 3 plus 3 plus 3 plus 3. Well, how many 3's are there? There's 5 of them. And that means you have a 3 5 times, or 5 times 3, which is the same as 7 to the 15th. I'm going to leave it in exponential form because we've seen how fast 7s can climb. So I'm going to leave this as 7 to the 15th power. What does that mean for y to the 5th to the 2nd? Well, if I was doing this the long way, I would take y to the 5th times y to the 5th again. That would be y to the 5 plus 5, or y to the 10th. And that's perfectly fine. But there's also this lovely rule that they gave us. And the rule says if you have an exponential expression being raised to an additional exponent there, I can take this as y to the 5 times 2, which is still going to give me y to the 10th. Do you see how I get the same answer? This is just slightly more efficient. It also works better in several situations. Here I have x to the 3rd times x to the 5th, and then I'm taking that to the 4th. I've combined a couple of different rules here. What we want to do is I like to work it inside first. I have x to the third, x to the fifth. That is x to the 3 plus 5, right? Same basis being multiplied. I can add the exponents. Then I'm going to take that to the fourth power. So this would be x to the eighth to the fourth, power to a power, exponential expression to another power I can multiply, x to the 8 times 4, which would give me x to the 32nd. You might be asking, Amy, when are we ever going to use an x to the 32nd? This is more about learning how to manipulate them correctly than it is the actual feasibility of ever using an x to the 32nd. We want you to be able to manipulate the algebra correctly. So while yes, you may never in the real world see an x to the 32nd power, it is important to practice how to get to that from x to the third, x to the fifth, all of that to the fourth, okay? All right, problem number 24 gives us the same kind of thing. Here I have a to the fifth to the sixth. That would be a to the 5 times 6 times a to the second to the 10th. That would be a to the 2 times 10. This would be a to the 30th times a to the 20th. The bases are still the same and they are being multiplied. That tells me I can add those exponents. So this would be a to the 30 plus 20, which would be a to the 50th. Right? Okay, we have one more rule, powers of products and of quotients. Basically, the power of a product and the power of a quotient. The power of a product says that if you have x to the m, y to the n, and you're taking that to the, I don't know what I want to use here. Let's use a p. We're using that as a p power. Notice the bases are different. The bases are not the same. The bases are different. That this would be the same as x to the p times m, y to the p times n. So literally distributing that additional exponent to both of the powers inside. Similarly, if we're doing the power of a quotient, if we have x to the m over y to the n, and we're taking that to a power of q, this would be the same as x to the qm over y to the qn. Notice again, my bases are not the same, so I'm not able to simplify this any more than I have. Okay? All right, so how does this work out with numbers? All right, number 25, we have 5x squared to the third. If I'm going to do this the long way, I'm not going to use this rule right now. I'm going to go the long way. That's going to give me 5x squared times 5x squared times 5x squared. Notice this gives me 1 times 5 times 5 times x squared times x squared times x squared. And I can move those around because it's all multiplication, and multiplication is commutative, meaning it is movable. This is the same as 5 to the third, x, and then I have 3 2's, or 6. 5 to the third is 125. X to the 3 times 2 is x to the 6th. This is how I would do it if I was backing it up and trying to do things using the rules I didn't know, I already knew. If I'm trying to use this rule, this particular pattern or shortcut, I'm going to run out of room. I'm going to do this. Okay, I am going to say that 5x to the second to the third is the same as 5 to the third, x squared to the third, right? Distributing this to both. Oh, but there's not one there. Oh, but there is a 1 there. Even though we never write it, that 1 is there. So that's going to give us 5 to the third is 125. X to the second to the third, I can multiply those together to get x to the sixth. Notice I have the same answer in a slightly more efficient manner than if I wrote all those out. Let's practice it again. Number 26, I have a to the second, b to the fifth. This is the same as a to the second, and b to the fifth to the second. Power to a power, a to the fourth, b to the 2 times 5 or 10. Power to a power, you multiply. A to the fourth, b to the 10th. For number 27, I have a negative 4f to the fifth, g to the second. All of this to the third. So that's going to be the same as negative 4 to the third, f to the fifth to the third, g to the second to the third. Negative 4 to the third. Notice that's in parentheses. So I'm going to do parentheses negative 4 to the third power. That's going to give me a negative 64. F to the fifth to the third. Power to another power. I multiply them. That's f to the 15th. G to the second to the third. Power to a power. I multiply them. G to the sixth. Negative 64. F to the 15th. G to the sixth. All right. So what does that do for number 28? Well, for number 28, that x over 5 to the third would be the same as x to the third over the 5 to the third. I essentially distribute that third power to both the numerator and the denominator. This gives me x to the third over 125. For number 29, I would have a negative 2g, or negative 2 to the third, there we go, g to the fifth to the third, over 5 to the third, h squared to the third. Negative 2 to the third, parentheses, negative 2, chevron key 3, that should give me a negative 8. G to the fifth to the third would be g to the 5 times 3, or g to the 15th, over 5 to the third. I think I'm going to get 125. Yep, 125. H to the second to the third. Second to the third, power to a power. I multiply 2 times 3 is 6. Can I reduce anything here? 8 and 125 don't reduce, so that's as far as I can go. All right, for problem number 30. I have r to the 8th, t to the 9th to the 3rd. Using the power of a quotient, this would be r to the 8th to the 3rd, and t, to the 9th to the 3rd. There we go. I had to keep that inside the parentheses. In the denominator, I would have r to the 5th to the 3rd, and then my other one would be t to the 3rd to the 3rd. Okay. Power to a power says multiply. So I can do r to the 24th times t to the 27th over r to the 15th times t to the 9th. Now, the bases are the same, so I can subtract. This would be r to the 24 minus 15 times t to the 27 minus 9, which is r to the 9th times t to the 18th. Whew. That'll work. That will for sure work. Now, let's talk for a minute, because maybe some of you saw it. Right? Maybe some of you saw that before If we just look inside of these parentheses, I could do r to the 8 minus 5 times t to the 9 minus 3, and then take that to the third. So that would be r to the third times t to the 6 to the third, or r to the third times t to the 6 to the third, r to the 9th times t to the 18th. See how we got the same answer? I don't particularly think one is shorter than the other. I do like this one a little bit better. Just because it's a little less messy. This one looks messier to me. But a lot of this is like what you see and the order in which you see it. There are often different paths to the same correct answer here. So the important part is making sure you're doing each step correctly. You're making a correct move with each step, not necessarily the order of the moves. Okay? It's a recipe, but it's not so important which order you cook it in, right? Okay. So on this particular sheet, I just have a summary of the rules that we've used for the exponents. The zero exponent and the negative exponent we're going to be handling in 5.2 in the next section. But this particular summary right here is a summary of the rules for all the exponents. These are helpful when you're doing the homework from 5.1 and 5.2. Right? Okay, I will see you in just a minute or two for section 5.2.